Hello, my name is Marina Medeiros. I am a researcher at VRVis Research Center in Austria and a PhD student at Vienna University of Technology. In this video, I will present our IEEE VR paper, Immersive Analytics as a support medium for data-driven monitoring in hydropower. The efficiency of power supply chains plays a key role in developing a sustainable future. Today, with the growth of other renewable energy sources, such as wind and solar, hydroelectric plants are also being used to regulate the grid according to demand. As a result, turbines sometimes operate at less than 50% of the power production for which they were designed. This can increase the need for repairs and shorten the system's life cycle. When to perform preventive maintenance, which operating conditions damage the turbine, and how to avoid damage under these conditions are still open questions for hydromechanic experts. Our virtual reality prototype is designed within the DigiHydro project. The project combines and compares simulated and sensor-measured data to enable data-driven predictions of the lifetime of the mechanical parts of hydroelectric power plants. It is coordinated by our partners from the Research Unit of Fluid Flow Machinery at the Institute for Energy Systems and Thermodynamics at the Vienna University of Technology. The idea of an immersive analytics application resulted from numerous conversations with these experts. Two factors made them interested in an immersive environment for data analysis: the possibility of visualizing and interacting with many plots of sensor-collected data at once, and the combination of abstract and spatial data, with the possibility to locate the data visualizations in the relative position of where they were extracted. After conducting a literature review, we decided to adopt a user-centered co-design approach with our project partners from the start. At first, we considered a situated analytics application using augmented reality to visualize data within the context of a real turbine. To explore this concept, we created an exploratory application that showcased various immersion levels for the experts. This application showed a 3D model of the turbine runner. Users could adjust the level of immersion by selecting different environmental backgrounds. In a first meeting, 3 experts interacted with the exploratory app and were introduced to the concepts of virtual, mixed, and augmented reality. The engineers rejected the idea of a situated analytics setup because the sensors are installed on operational turbines that are not always easily accessible. They defined the use case of VR application to show a combination of abstract data from simulations and sensors in context with spatial data. In the following 4 meetings, we held short demonstration sessions to present earlier versions of the application and get feedback from the engineer coordinator of the DigiHydro project. In the last phase, we developed the version of the DigiHydro VR application that was evaluated in a qualitative feedback user study. DigiHydro VR was developed in Unity. It was visualized in a MetaQuest 3. To create the data visualizations, we used the Immersive Analytics toolkit from Cordell et al. The prototype combines the spatial data of a 3D model of a hydroelectric turbine and 2 types of abstract data: flow streamlines derived from simulations and pressure sensor data extracted from a real operating turbine. The sensor positions are marked with yellow spheres. The user can fly through the model walls and navigate through the data points. The flow streamlines visualized come from water flow calculated with computational fluid dynamics simulations. 3 different operation conditions of the hydropower machine were presented. Called part load, the machine is operated to produce only 50% of its total capacity. Operating a machine in this state generally leads to water turbulence and increased machine damage. The machine is operated at 83% of total capacity. This is considered to be the optimal operating point for the model of the hydropower turbine used in our project. Called overload, the machine is operated at its maximum capacity. This produces the maximum amount of electricity possible, but also leads to increasing wear and tear on the machine parts. The sensor data collected by the pressure sensor were extracted from a longer time series. We only considered time periods where the turbine was operating under conditions similar to those used for the flow simulations. We performed a fast Fourier transform to calculate the amount of frequencies of the pressure values. We visualized the FFT data in 2D frequency plots. that is, histograms, with one bar for every frequency found in the data. Users could access the sensor data in two different ways: at the location of the sensor in the 3D model. A button in the menu allowed users to open data of all sensors in a certain operating condition. Users could make copies, delete, and manipulate 2D frequency plots for data comparison. Our qualitative feedback interviews were structured around three objectives: understanding how the data from the sensors and the simulated data is currently analyzed, addressing the potential of the immersive real-scale environments with the position of the sensors to support the understanding of fluid phenomena, understanding the potential of VR for data analysis in the operation of hydroelectric power plants and related activities. 9 engineers used the application and were interviewed individually in sessions lasting between 45 and 60 minutes. We conducted semi-structured interviews, supported by an interview guide with sample questions organized around the three objectives of our research. Domain experts can gain more knowledge by specializing in one specific task or acquire a broader understanding of processes with time of work. This is translated from the comments and criticism received from the experts that we interviewed. Experts that works mainly in CFD simulations or with CAD models have already a better spatial understanding of the turbine and ask for features to speed up navigation. Experts that works primarily with analysis of data from the sensors mentioned many issues with the plot's visualization in VR. More experienced engineers explored more features of the application and drew more conclusions from the data analysis. Combining both spatial and non-spatial data added value to the application. Experts found it particularly valuable to explore spatial relationships within the data. This combination gave them a clear, more overall view of the project. The immersive environment was praised for improving the visualization of certain details. Our analysis confirms the value of immersive analytics applications for presentation purpose and suggests that the combination of spatial and abstract data in VR applications can also have great educational value for the field of hydromechanics. Our work suggests that using immersive analytics as a medium for problem investigation would create a context of use and potentially encourage domain experts to adopt the technology. Our interviews show that an expert, although with the knowledge to interpret the data, might not see the value of an immersive system when having just a partial engagement with a highly domain-specific use case. Domain experts are unlikely to use immersive solutions if their routine tasks of checking data does not point out to any problem. Therefore, immersive analytics applications should be envisioned as an extension to desktop applications already in use. Presenting basic virtual and augmented reality principles for an exploratory application proved to be effective. The experts confidentially choose a VR setup for the application. An effective methodological decision was not to ask experts for the feedback on the interaction design, but to focus meetings on data types and their representation. In phase 2 of our user-centered design approach, we only had feedback from the project coordinator. This is reflected in some criticism of our application by the younger experts that work in more specialized tasks. In our future work, we intend to include participants with different levels of expertise in all designing phases. In summary, our main findings are: the combination of spatial and abstract data in an immersive environment gives a complete overview of the underlying problems of the field. Immersive analytics shows great potential for education. It could be used for inspecting specific maintenance issues. Domain experts are very specific about their work routines and problems, and immersive analytics applications should take this into account to avoid skepticism. Thank you for your attention, and please read our paper to learn more about our work.